afternoon to all of you. We welcome all the people who are connected with us at this time, and we thank you for participating in this webinar that we do in alliance with NovaCep. I introduce myself. My name is Victoria Vergara from Caña, and today I will be accompanying you in the moderation of this webinar, and I am going to tell you a little bit about the dynamics we are going to have today. Okay, first, I confirm that this conference is being recorded to be sent later to the registered people. So, we are going to have the following dynamics. Today, we are going to be with Oscar and Philip, who are going to be accompanying us as speakers. And after each one makes their presentation, we are going to have a question and answer session. This way, so that you can interact with us and share with your questions via chat and via voice. Through the chat, you find a toolbar at the bottom of your screens where you will find an ellipsis, and there you find the chat. In that chat, you can write your questions to us, and we will be sharing these questions in the session. Additionally, if you want to participate by voice, you can find a button on the same task bar at the bottom of your screens that says reactions. When you select it, the option of to raise your hand appears. Then you raise your hand, and in this session, we will proceed in order in which each person raises their hand to give them space to ask their questions. So, I give the floor to the first speaker today. Good evening, Oscar. How are you? Good afternoon, Vicky. Thank you so much. I'm doing well. Before we start, can you hear me well and can you see my screen? Yes, we can see your screen and we listen to you well. Perfect. Okay, good afternoon to all the participants. First of all, I want to say thank you very much for connecting with us today and to the people who are connecting again. Thank you for participating in the second webinar today made by NovaSet. Today's topic focuses on the liming process, which is the use of calcium oxide to remove impurities, and also the softening process, which is the removal of calcium and magnesium in the production of sugar. We will talk about these processes with two sources that we have in mind: the beet sugar source and the sugar derived from cane. We divide this webinar in two sections. First, we will talk about the beet based process, and the second, the cane sugar based process. We will have a question session after each session, more or less 5 to 10 minutes, so you can ask your questions. Well, before getting into the subject, let me just briefly introduce NovaCep. I want to tell you that NovaCep is a French company located in France, in Lyon, and NovaCep's focus is to provide purification and separation process solutions, normally with processes in liquid form. We have a global presence. The main office is in France, with important offices in the United States and also in China. We serve biotechnology industries, including food ingredients such as sugarcane, functional ingredients such as fructooligosaccharides, uh, fermented based chemicals such as amino acids, and other industrial chemicals. Well, what are we doing? We offer process solutions with our key technologies, which include ion exchange, ceramic membrane filtration, and also industrial continuous low pressure chromatography. Our solutions are not only for large scale equipment. Our business model is based in helping and creating value from research and development to the commissioning. We have the staff and the laboratories to be able to take a project from the laboratory study to the industrial commercialization. Now, let's get into today's topic, which is the sugar juice softening topic. First, it is good to keep in mind how the raw material for sugar production is distributed in the world. In this map, we see that beet crops are more localized throughout the northern hemisphere and sugarcane in the southern hemisphere. And there is a combination of beet and sugarcane crops in between in the area of United States and Central Asia. With this in mind, let's remember that today's conversation is about the softening of cane juice, sugar juice. We have to ask ourselves, why is softening important? The answer is actually very simple. The hardness, the presence of calcium, magnesium, and other minerals in the juice creates a problem because when the juice has this type of hardness and enters the evaporation and crystallization stage, there is a negative result in the operating part and in the commercial part of the plants. Mainly, these minerals precipitate in the evaporator area, causing a build up of carbonates and oxalates, which we call incrustation. Here we show some images. There are examples of this incrustation phenomenon. This build-up decreases the efficiency of the evaporator and the quality of the final product, something we will discuss in more detail later. So, now we will talk more specifically about this softening process as it has to do with the production of sugar from beets. My colleague Philippe, who Vicky introduced, will speak later in the second section about the sugarcane washing process. Well, let's start with this diagram that explains the large scale process of sugar production from beets. On this occasion, we are not going to cover all these steps of this process. In reality, we are going to focus on this section, which would be the juice clarification section. But in general, what has to be understood is that we start with the raw material, which is the beet. Here are certain processes of storage, cleaning, cutting, and then we come to the clarification process, which is the important process to reduce the dissolved and sustained impurities in the juice. Okay, let's go now into more detail with this liming and carbonation process, which together we call the clarification process. In the liming process, which we see here in this diagram in English, those are the stages where calcium oxide is introduced. In English, it is called limer. Calcium oxide is added, which becomes hydroxide of calcium when is mixed with the juice. This process increases the pH. Then we have the carbonation stage that occurs in two steps. The first step, then the second step. And in this step, carbon dioxide is introduced to reduce the pH and to induce the precipitation of calcium carbonate. These combined steps are part of the purification process, or what we call clarification, which today is the most effective and uh, less costly that is based in these type of plants for the production of sugar based on beets. As we talked about earlier, the process of carbonation is a introduction that is divided into two steps. The first step, the objective, is that the juice has a pH higher than 11 and to keep the temperature at 20 Celsius degrees. And the ultimate goal of this step is to remove many impurities, including invert sugars, colloids, pectins, organic acids, color. Well, in conclusion, what we want to do in this step is to increase the purity of the sucrose at to a level more or less of 85 to 95%. In the second carbonation step, here what we want to do is to reduce the pH a little while keeping the temperature the same. And what we want to do is while we manipulate the pH to be able to change the residual calcium concentration in the juice. And we want to minimize that calcium content in the juice. Well, now let's talk about, well, okay, those are the advantages, what we saw here. Now we are going to talk about the downsides. What is the downside or what are the downsides of this liming and carbonation process? What I want to highlight first is that we introduce calcium in this liming process and we can see the calcium levels in the different parts of the process. We start with 10 grams, then we lower it to a gram after filtration, and then in the second carbonation step, we still have residual calcium. What is the impact of this residual calcium? Okay, the impact is that now we have a clear juice, but we have a hard juice, a juice with hardness. More or less, this concentration of calcium can be transformed. I don't know when it is moved to 50, maybe from 50 to 500 ppm of calcium per liter in the juice. And what happens then is that when we have this type of hardness, obviously we are going to have incrustation problems later in the process, in the evaporation stage. If these calcium salts are not controlled, they precipitate during evaporation and the incrustation phenomenon is formed. What is the impact of incrustation? Okay, the impact has to do with the heat transfer coefficient. Well, there is quite a bit of information in this slide here, but in short, the coefficient drops when you have more and more layers of incrustation, and this results in higher stem consumption as the evaporator is not working efficiently. This is the result in reality when you have incrustation and mineral deposits in the crystallization evaporation equipments. The equipment will not work 100% efficiently, and more water vapor will be consumed in the plant. Additionally, what are other impacts of these calcium residues? Well, here on this slide, we have summarized four additional impacts. In summary, the first three, the 3 points that are summarized here are negative, and the last point is positive. So let's talk about each one. The first one says that calcium salts are absorbed into the crystals during this process, and the result is the reduction of the crystallization kinetics and also the increase of turbidity in the crystals. In other words, the presence of calcium increases the turbidity of the sugar crystals. The second point is that the calcium salts increase the viscosity of the mass quid, which in conclusion increases the amount of molasses produced in this crystallization process, while increasing the amount of molasses reduces the sugar yield from sucrose. The third point is that calcium acts as a transporter for the colorants, which affects the final color of the product as well as decreases the quality. And finally, this is a very interesting point because it is a positive point, but at the same time, when combined with the other negative points, the total effect is negative. But it is very interesting to note that the presence of calcium has a positive effect, which reduces the solubility of sugar. This facilitates the crystallization of the sugar and increases the yield of the sugar by the crystallization. But as I have already said, it is a benefit that usually does not outweigh the negative effects that were mentioned in points 1, 2, and 3. Okay, how do we solve this hardness problem? This is where we start to introduce this softening process. The softening process, as it is. We solve this calcium problem in this bead process using an ion exchange based solution developed by Novacep, and this product has the name of NRS. This is a product offered by Novacep. It is a very innovative process where there is no use of chemical regeneration, there is no use of water for rinsing, and no loss of the final product. That means there is no negative impact on sucrose yield. Additionally, it is a solution that solves the incrustation problem, which generates great efficiency in the use of stem for evaporation and crystallization. It also generates a better yield and quality of the final product since the final crystals will have less turbidity and less total molasses will be generated. The process is based on the use of a cationic resin that it has been strong and is in the sodium form. So the clear juice with hardness passes through the resin and the calcium is exchanged for the sodium generating and exit stem of softened clear juice. When it is time to generate the resin, the softened juice is used instead of regenerating chemical for regeneration. The temperature of this softened juice is lowered and the pH is raised a little with a little bit of caustic soda to generate a precipitation reaction of the calcium that is absorbed in the resin. And the precipitation occurs by transforming the calcium into calcium sucrate, which is very soluble in the juice and is displaced from the resin, and the resin enters again the sodium. This effluent contains calcium and sucrose, which are recycled back at the beginning of the process. Here we see this is the effluent outlet and the recycling is shown is this diagram. In conclusion, it is a very green and efficient process. At the end, the resin is rinsed with a hot softened juice and the resin is again ready to be softened again. The last thing I want to mention on this slide is the scope of this technology NRS that okay, here we are only talking about the reduction in average terms. The residual calcium is reduced to this range 5 to 10 milligrams of calcium oxide per liter of juice. That is the scope. Now we are going to talk a little more about the general numbers, but based on our experience and on summarized data from production plants where we have worked and we have placed examples. So here in summary, in a summary case study format, here we are talking in this case study of a factory capacity of 10,000 tons of beets per day that are produced, that are processed. Here we see the level of reduction of calcium in the juice. We start with 150 milligrams and reduce it to 15 milligrams with the use of NRS technology. The exact time of the beat is 120 days. And here are other operating cost figures. The caustic soda that is used to supplement the regeneration is 2.2 tons per day. And here are some estimated costs. We also include in the operating costs the change of resin that would be made in each harvest. Now, what are the benefits? In this first section, we have potential benefits in what has to do with the environmental footprint, and we have 3 points. In the first point, we have the elimination of soda ash or sodium carbonate, which is normally the chemical that would be used as a form of chemical softening. But with the use of the NRS, it would not be necessary to use this chemical. Similarly, no anti-incrustation chemicals have to be used because once the juice is softened, this is not needed. And what we see here are estimated costs that would be eliminated with the use of the NRS. In addition, the impact of not having incrustations on the evaporators results in the elimination or reduction of the chemicals used for cleaning the evaporators, and obviously also for the effluents generated by these cleaning chemicals. Well, what are the advantages or improvements in terms of quality and performance? In order to summarize, in this case study, the turbidity is reduced below 10 to 15 IU, and the color is reduced by approximately 10%, and the molasses production is reduced by 5 to 10% in this case. Now, in terms of return of investment, in summary, the typical return of investment for this type of project for a traditional plant is 2 to 4 years, depending on the conditions of the plant. Here are some key points that make this solution even more favorable and increase the return on investment. So the points are that when the calcium concentration is higher than 100 milligrams, this creates a favorable condition. Likewise, when we have a long harvest instead of a short harvest, the return increases even more. If we already observe high turbidity in the sugar crystals, if there are active projects in the plant to optimize the distribution of stem in the evaporators, and also if the plant has in mind or already has installed equipment to recover sugar in molasses by chromatography. This solution, when using NRS, generates molasses that does not contain calcium, which is more favorable for the chromatography process. And the last point we make here is that for new projects, what we call greenfield projects, the investment cost is a very small percentage in relation to the entire investment cost to to build a new plant. So making the decision to put in a softening kit is a very logical one. Now, we end this section with some reference data for the use of a softening system, such as NRS. These data are for the European region, but they can also be expanded for the North American region. In summary, of all the beet-based sugar plants, approximately 40% of them implement a softening system. Additionally, of this softening system, more or less 80% have NRS equipment, which is from Novosep, which is a very high percentage in the market. And with this, we end this section talking about softening for the bead-based process, and we can enter the question and answer section. Perfect, Oscar. Thank you very much. We start with first question, and it is: what are Novocep's industry benchmarks for NRS technology? Well, Novosep has a very large base of projects that are already in operation. We have more than 100 units that are operating all over the world in the places shown on the map. Well, I think the data we also have is that we have this type of installation in the largest plant. It is the sugar plant based on beet found in Egypt. And finally, I have here some reference information. We have more or less 10 references in China, 50 more in Europe, 10 to 20 references in the United States, and in the Middle East, we have about 10 to 20. Perfect. Let's go to the second question, and that is there a negative effect of having sodium in the syrup? Well, interesting question. The answer is no. There is no negative effect when having sodium in the final product. Speaking of the crystal, the sugar crystal, the sucrose, because during the crystallization process, the sodium will go with the molasses and the sodium will not be observed in the crystals. But additionally, it is very interesting to highlight the point and how, as I said it before, that the presence of calcium actually creates a benefit in the crystallization step. But even when we remove that benefit, when we remove the calcium from the crystallization and replace it with sodium, in theory, it should decrease the yield of the process. But in practice, because it is what we have studied, we have observed, in practice, the result of removing the calcium has a very positive effect on the performance and quality of the final product. So, in general, the answer is no. There is no negative effect. Perfect. Let's go with Fernando's question, who says, what experience do you have in the cane sugar industry and what pH is managed? Well, for this question, this is a question about sugarcane, right? Yes, it is. So I think we would have to wait to finish the next section that is going to talk about cane sugar, and there would be room for that question. Perfect. there is one last question, and so we continue with second case. And the question is this type of sugar handled or managed in Colombia? Okay, I believe I want to tell you that in this webinar we have an expert with us in the area of beets and also sugarcane, who is a part of Novasep. His name is Francois, but I think the answer is no. We don't have beet plantations in Colombia. But Francois, I don't know if you would like to answer the question or if you want to make other comments. No, I think that as you said, it has to do with the zone in the hemisphere. In Colombia, I think that there is only cane sugar production, refining, but there is no beet sugar factory. I think there are some factories in Pakistan, in some Middle East countries that use cane and beet, like in Egypt. That beet is on the seashore and cane in the south of Egypt, for instance. Some countries have both industries, but Colombia. Okay, thanks, Francois. Here, Francois confirms that the answer is no. It is not an area where beets are grown, but perhaps the question is also trying to uh, question to ask the question of whether this type of technology is used in sugarcane, and that is exactly what we are going to talk about in the next section. Perfect. Cyril raised his hand. He's also from Novosep. Yes, excuse me, Vicky. It was just to confirm exactly what Francois said. I think we will see it in the second part, but it is important to note that this technology that exists, which is very robust, that Oscar presented, was also demonstrated and approved here at the semi-industrial level in Colombia through industrial testing trials that we have carried out on a pilot scale. So there are no reference because there is no beat in Latin America. Perhaps in the Chilean area is where there may be a little, and also as Francois said, it exists in other countries. But this technology was approved, and that is why today we are going to present what we developed as a design applicable precisely to cane sugar, to sugarcane. Perfect. Thank you very much, Cyril, Oscar. Now we continue with the second case. Then I'm going to stop share my screen. Please, we remind you that you can share your questions with us through the chat, also by raising your hand. After the second case, we will have another question and answer session, and we will proceed to share these questions. We will also answer the questions that remain pending via email. So, we give the floor now to Philip. Thank you very much, Vicky. Good afternoon, everyone. Well, I'm here today to talk a little about our technology in the process for the softening of the sugarcane juice. Every day, millions of kilos of cane are processed for the production of sugar, and the raw material is processed through several steps that involve mechanical and chemical treatments or processes, as we can see in this flow diagram. We know that the hardness is caused mainly by the presence of calcium and magnesium. Thus, if we look at this diagram here, we can see that uh, added to the natural calcium and magnesium content of the cane in the clarification stage. Specifically in the lime, we are adding calcium and magnesium salts, and these increase the hardness of the juice. At the end of the process of this hardness, we are responsible for the incrustations in the evaporators. This mineral layer that forms in the evaporators constantly recirculates and interferes with the heat exchange capacity in the system. As a result, too much evaporation and more stem is required to keep or to maintain performance. and several shutdowns are required for periodic maintenance when stem consumption can no longer compensate for performance losses. Thus, in some places in Latin America where we have very high hardness measures, it is often necessary to make several stops a day. Well, if we look more closely for the purification stage and compare it to the beet process, we notice some important differences. In sugarcane, the liming process and the phosphating process are generally used rather than carbonation. This process is cheaper, but it is a process, a less effective process. Thus, we can have sucrose purity in the juice of 83 to 90%, depending on local conditions. And also, this cane juice has more impurities present, mainly due to the presence of bagasse, calcium salts of magnesium, dextrans, starch, also polysaccharides, wax, and coloring agents. So, when we work with cane sugar refining with yes, cane sugar refining without carbonation, it is not possible to remove the magnesium salts and also the precipitation yields. In this case, it is lower. We have a higher residual hardness content, and the calcium content can vary between 500 and 2000 ppm, and the magnesium content can vary between 200 and 550 ppm. Here, for the production process, also that of the cane and beet, it is important to note that in cane harvests are 2 to 3 times longer compared to beet, and due to the clarification process used, you always see a lot more calcium magnesium salts in beets. So that in the cane it is necessary to increase the frequency of cleaning of the evaporators, and as consequences, operating costs increase due to the higher consumption of chemical products and energy. If we look at the evaporation diagram here on the screen, we can see that vapors are produced after each stage, typically after each evaporation stage, and that the energy of the stem when working with an incrustation system is smaller. So, compared to beets, cane cannot be used in evaporator 3 for the process in evaporators when we are working with a clean system, as in the case of the cane application. We can change evaporator 2 to evaporator 3 so that we have more economy, more savings if we have energy in the process. We can also note that the impact on these crystallization differences is that raw sugar is generally produced in cane with a higher color type and low purity, and many times a sulfation stage is used to compensate for that higher color. Then sulfation is used to remove the color from raw sugar, but it is important to be careful because this process can lead to an excessive amount of sulfites in raw sugar. Now we are going to talk more specifically about CSF technology. So, with these problems in mind that happened based on the technology previous presented by my colleague Oscar, Novasep developed an afflection CSF technology to reduce the hardness of cane juice. And our technology consists of a combination of a filtration step in which we remove the what we don't want from the juice. Then the bagasse, part of the moisture, part of the polysaccharides with an ion exchange step that is responsible for eliminating the calcium and magnesium ions. This process is ecological because we do not use water, we do not use chemicals, and no effluents are produced. We can also notice that we have more energy efficiency for the process. So, how do we make this process perform all the functions without using the same condition? In every cycle, when the line is saturated, it is necessary to make a stop in a specific part to facilitate and also help the line. So, for these steps, we do not add the same conditions. We only recirculate those that we already have in process. So, for cleaning, we recirculate a small radius of decalcified juice so that the sludge produced has been recirculated and processed for a better process. To regenerate the resin, we use molasses B or C depending on the process. It is important and necessary that it be decalcified molasses, calcium and potassium ions. So we recirculate these molasses, we recirculate it in the column by means of ion exchange, taking into account that the calcium and magnesium ions that are encrusted in the resin are released so that we are going to produce a molasses with calcium again. And it is important to know that this molasses that we produce here has the same chemical composition, the same ion charge or load that the CSF system had, and can therefore be used again for the production of ethanol. This process was developed and adapted for production to be applied in the sugarcane industry. And during these stages, we worked on the development of this technology, and we had several pilot tests that we carried out in Brazil and Central America. And today we have a very robust process and a design ready to be installed on an industrial scale. So, what we're looking for are for clients and people who want to discuss with us the application of this process and its application in your sugar mills, in their sugar mills. So we did a case study to show the benefits with that we have with the application of this technology. I would also say that the efforts are currently being made to improve the energy efficiency and optimize industrial processes. And also, with the arrival of Industry 4.0, the stability is that is gained with this process allows this technology to be a perfect complement for modernization in the sugar factories. Now, I would like to show you a case study that we did for one of those pilot tests. Then it was a place that has a capacity of 2,000 tons of cane per day and a high residual hardness in terms of 1,400 ppm. And in the pilot tests, it was possible to have a very efficient reduction in hardness. So the hardness of the softened juice was less than 276 milligrams of calcium. Apart from this data, it was possible to dimension the industrial level, and with this, we simulated what the operating costs would be for that plant. So the most significant cost was the exchange of the resin that had to be changed for each harvest or every two harvests, depending on the local conditions. We also did a study of what the benefits would be with this technology. So we can see economic benefits that we have with the reduction of the energy costs of the plant. We also have a reduction margin in the number of clinics. So we have less chemical consumption for the generated effluents. There was also less effluent generated for cleaning evaporators. The evaporators and another factor that I see here is that we have more gain in the quality of the sugar produced because we have significant reduction in turbidity and soluble salts of juice have a better sugar quality. Another important factor to consider here is that when we make the crystallization of sugar and a juice that has less calcium, it has an improvement effect because today a calcium, when it goes to crystallization, tends to be absorbed, and this way the crystal has a more turbidity, and they tend to work as a transporter of impurities for the crystals. In this way, if we crystallize a calcium-free environment, we have a better quality sugar with less crystal turbidity. In order to use this technology, it is very important to have a good interaction of this technology with the customer process. So for each factory that has its own configuration and characteristics, a detailed study of each case must be carried out. Now, let's talk a little about what would be those factors that impact and influence the return on investment time for the installation of a system like this system. The first factor that we consider would be the calcium residue that is in the clear juice, because depending on the hardness, it will directly impact the system that we must design for your side for the meal. So the greater the hardness, the greater the system, greater amount of resins needed. So it is an important factor. Another important factor is the time that the harvest lasts. Generally, what we see is that the longer harvests have a shorter return on investment because they have benefits for a longer time during a year. Another important factor is that depending on the quality of the sugar in the meal, in the plant with this system, a higher quality sugar can be produced. So if there is a profit in terms of the price that is in this sugar sold, so we have a higher quality in sugar. It is a technology that can help a lot to obtain a better quality sugar. Another gain that we have is in analyzing how we can optimize the distribution of the stem in the evaporators. Then the system that we have, for example, has a backup of the evaporators so that the evaporators are um, always in operation, or when the evaporator is are in cleaning process, or simply that are evaporating to the capacity limit. So with this system we can optimize the vapor distribution and the evaporators and thereby increase the evaporation capacity. Then it's possible to increase the sugar production capacity with the same structure that we have today. Also, another point that is important is that when you have to increase production capacity, or if you are going to build a new production line for implementation of a new mill, it is a very important technology to be considered because it enables stem optimization in the evaporators. It already makes it possible to have these improvements in the new projects so that there is a more optimized capex for the plant or mill. Typically, what we do is that for the elaboration of this technology, it takes between 2 to 5 years, depending on the conditions of the sugar factory. But generally, with the factories we have worked with, it shows that the return of investment is closer, more or less 2 to 3 years or 2 to 4 years than 5 years. Here we have a reference of to a factory where this system is currently. So this photo shows a system that was installed in Hawaii. It was a small plant that operated for 4 harvests, and the calcification system at that time it has a difference that it was worked with ceramic filtration instead of filtration for a sludge. I'm sorry, just treatment or processing, and that ceramic filtration was a very efficient process which was used for aggregate with decalcification, but it is a more expensive technology, so the cost of implementation is higher. What was verified at that time in our project is that during the plant's operation time a higher level sugar was used, and cleaning stops can also be reduced and energy consumption is optimized. But at the end of the 90s, this plant stopped operating because they sold sugar for a refinery in the United States, and this refinery did not pay a good sum for liming sugar, so they stopped production at that time. Now the second reference that I am going to show you is a reference that we have developed in recent years, which some pilot tests that we did in Brazil and Guatemala. Here we can challenge our system against juices with very high hardness, and it was also very efficient. But in order to optimize the implementation of the system, we changed the ceramic filtration systems for a frontal filtration system that proved very efficient also for removal of impurities in the juice. So we also had the reduction of the turbidity of the sugar. We also had reduction of starch, and it was possible to see that the sugar produced was of superior quality as well. But here we only have pilot tests. We do not have a system installed on an industrial scale. It is hardly on a semi-industrial scale. Here we now have a photo that I want to show you of what an industrial scale ceramic filtration system would look like. Here I also want to show you the whole system of a frontal filtration system on an industrial scale. We also have that system, and finally a photo of an industrial scale ion exchange system that can be used for both beets and sugar cane. Thank you very much for your time. I thank you for having connected to this webinar. And as a final message, I would like to tell you that we currently have a very well developed process and ready to be applied on an industrial scale. So I hope that those interested in this technology enter into contact with us, and we can discuss this technology in more detail. And we can also see a design for your meal so that we can show you the benefits of installing our technology, since it is a very robust process and that will bring you many benefits in your process. Thank you. And now we will be ready for the question and answer session. Perfect, Philip. Thank you very much. We start with this second question and answer session. And our first question is: could you comment on why juice softening is nowadays a more widely implemented technology in sugarcane processing mills? Well, I think that at this moment we do not have many systems installed in cane. What happens is that this technology is the technology that we use in the Hawaii plant. It uses this ceramic filtration system, which is a more expensive system. So then the capex for these plants was higher, but in recent years we have worked a lot to improve this technology so that now we have a more optimized solution with a cheaper implementation cost with the operating system. So I believe that now we have many systems installed also for sugar cane. Perfect. Okay, we continue with the next question, and it is: could you comment more on the real energy savings and sugar quality with CSF technology? Of course, it is a very important question, and we can consider that in the system we have a combination of filtration with an ionic charging system. So this filtration is responsible for removing the turbidity and also the soluble parts that are in the juice that the juice has. And this removal has an effect that is reducing the compounds that generate colors and also transport ashes with the sugar so that we have higher quality, and we also have an effect of the way the sugar crystallization is done with without the presence of calcium. There is no such presence of calcium or impurities, so we have less turbidity in the sugar crystal. We also talk about saving energy. They are some factors that we can have. So we have the fact of the way that we are working with the evaporators to have cleaner processes. We have a thermal load efficiency since we have less energy use, but also on how evaporators are cleaned and less. It is not necessary to stop the process in the plant so often so that we have stability in the process, and with that stability is necessary for the plant to start again, so it is more stable process. It tends to consume less energy, and we also have the possibility to optimize the use of energy and stem in the plant when working in the plant with the system that has the evaporators, the energy. We have a third effect of the evaporators that is not so great. So it is not enough to be used in order to heat up the crystallization rates. Then it is necessary to use it for two. In this case, we can send for stem 3 because it would generate a great energy savings in the plant as well. Those are the main three factors that impact on energy savings. Perfect, Philip. Well, let's go with the next question. The question is there an impact on the magnesium and calcium content for fermentation? This is an interesting question, and it is also a frequent asked question that we are always asked. There is no impact because if we consider that the system is working as if it were a bypass for the hardness, then we have the hardness when the juice passes and the hardness for the molasses for regeneration. We have no addition of calcium or magnesium in the molasses. So the calcium and magnesium content in the molasses after the CSF is the same content as it was with the previous system. So this molasses can be used for fermentation in the same way and has the same impact as previously without major problems. Perfect, Philip. Let's go with the last two questions. And one is from Hector Osuna, who asks what other impurities apart from calcium and magnesium can harm the processes already explained. Excuse me, I couldn't understand the question. Could you repeat the question? I couldn't hear it. No problem. What other impurities apart from calcium and magnesium can affect the process explained? Okay, in this case, we have the presence of impurities in cane juices. We have the gas, we have a high content of strands of starch, we have a high content of polysaccharides, of wax. So these impurities can have a negative impact on the resin. But as we always use filtration systems before the ionic load or charging, this system protects, removes these impurities so that these impurities do not impact crystallization, and also the way we are removing these impurities of the juice, it would not impact the crystallization of the sugar later on, and we also have a better quality. Perfect. Diego asks, could this technology be used in clarified syrup, thinking of reducing salts that impact crystallization? Excuse me, I didn't understand the question. Can you repeat it? Could this technology be used in clarified syrup, thinking of reducing the salts that impact crystallization? Well, in theory, it can be used, but integration into a system might not be as efficient. Antoine may have a comment related to this. Well, I think that maybe there is a little confusion with the technology. It is not a system that is going to process or treat the syrup. It is a system that is going to be fully integrated first with the juice, and it is um, then it is going to make a syrup, which in principle has no hardness. This syrup is needed to regenerate the resin, and in the end, the resin will have hardness. I think that the person who is asking this question may think that we should process the syrup, but that is not exactly what happens. Perfect, Antoine. Thank you very much. Okay, let's go to the next question from Luis Fernando Huitrago, and he says, can this process reduce the dextrans that go into the juice, and how much can the reduction percentage be? Yes, it is possible that it reduces the dextrans that go into the juice. This depends a lot on the composition of each juice. So it is something that we have to validate on each plant to be able to see. But if it were a plant with a lower capacity and we used, for example, a ceramic microfiltration system to process the juice with that, in this case, we would be having a 99% reduction in destrants, more or less. But if we use a frontal system, reduction would be less. We need to validate depending on the composition, the profile of the contaminants that the juice has. Okay, now the final question is, what is Novacep's industrial experience with the CSF process on offer? Okay, we have an industrial reference of a plant that was installed in Hawaii, United States. This plant worked with 4 harvests, but if we produce a quality and the criteria of each plant does not have an economic benefit with the sale of sugar at the end, so it was very good for sugar. but when negotiating sugar with the refinery, it was not paying more for this process, so the plant stopped producing sugar from harvesting, but the technology in the plant worked very well, and it was possible to verify all the internal benefits that we obtained during the process, during the cleaning of the evaporators and the other benefits that we discussed previously. Okay, Philip, thank you very much. We end with this session and of questions and answers. We thank Antoine, Philip, Oscar, Cyril, and also Francois for joining us at this Novasep event and sharing this knowledge with us. To the people who could not give answer due to time issues, we remind them that we internally take their questions and we will share them with our presenters to be able to answer them via email. We thank everyone for their participation. We remind that the conference is recorded and will be sent to you later. Many thanks to all the presenters of NovaCep for joining us. Philippe, Antoine, Oscar, Cyril. Thank you very much, Vicky. Thank you very much to all of you. Okay, thank you very much to all of you. And any communication you need to have with Tecnicaña, you can write to us at capacitación at tecnicaña.org in case you want to share these additional questions with us.